Very good morning, good afternoon, good evening, my dear friends and students. This is the Total Quality Management 1 course, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. I am sure you know my name by heart by this time, but still, as an introduction, I start with that. So, we are, as you know, considering the study of the charts, which are basically X bar and R charts. And we did discuss in some details that if mu, I am just going a little bit back to the 24th lecture and something to the 23rd lecture. It is just a recap. We did discuss about the charts, only two charts, based on the fact that mu and sigma are not known, and in other case we consider the mu and sigma are known, and if they are not known, what are the best estimates we can use from the sample. And also the coefficients, which were basically either 3 or 2, it is not exactly 2, but or 1, they would depend on what is the overall coverages which we have, whether it is plus minus 1 sigma, plus minus 2 sigma, and so on and so forth. And based on that, you will find out that why we had taken those values of A suffix 1, 2, 3 or B suffix 1, 2, 3 or the D's values which we saw from the tables. That means, again I am repeating, the values of sample size you had on the first column, and all the rest values were depending on the parameter values of the coefficients depending on the sample size. Later on in the fag end of the 24th lecture, I did spend about 10-15 minutes of trying to basically give you some feel that where the patterns can be understood. Those I mentioned from the so called theoretical point of view, but obviously if you are working on the shop floor, you will understand. So, those set of informations would be useful to understand that how the patterns, cyclicity or stratification or trends would be there, which will give you some informations of both the X bar and the R charts. So, now we will consider the S charts. So, it is an occasionally desirable to estimate the process standard deviation directly instead of indirectly using the R charts. And if you remember, I did mention that if mu and sigma were not known, then what we did was replace mu with the concept of X double bar, and if sigma were not known, we used the range and used the calculations to how you can find the best estimate of the standard deviation using the range. Later half we consider both mu and sigma are known, and we did the calculations accordingly. But what is more important to understand is that whether we can use the sample standard deviation or the sample error or standard error from the sample as the best proxy or the best set of informations based on which you can find out the variability of the total population and draw some meaningful conclusions from that. So, that is what we are trying to understand now. So, let me continue reading. It is occasionally desirable to estimate the process standard deviation directly instead of indirectly using the range. So, S chart is favored over R charts when the sample size is n is moderately large, say for example greater than 10 or 12, and the sample size n is variable, in the sense that in the first case due to some reason early 9 o'clock in the morning I am able to take 7 observations. Then again in the about 1 hour from then, which is 10 o'clock in the morning, I do not take the same set of observation, but the sample size has increased to say for example 20. So, if it keeps fluctuating, then trying to use S would make much better sense than trying to use the R, but the actual essence remains the same. I want to understand the variability of the overall production process, whether I use R or S would basically be the question. So, the operating characteristic functions would be important for us to study. The ability of the X bar and the R charts to detect shifts in the process quality is desirable by the operating characteristic curves, the OC curves, where we have the LTPD, AQL, alpha, beta and all those things. For an X bar charts, if the mean shifts from in control value, say for example is changed from mu naught to mu 1, so there can be either positive or negative, forget about that. The probability of not detecting this shift in the first subsequent samples is basically a type of error which we generally term as the risk, which is alpha and beta. Now, what we want to find out is that whether the pattern of shifting based on the change of the mean values does have an effect on the overall risk. Now, the word risk we use about the total loss, but that risk can come either from the positive sense or the negative sense. What we mean by the positive and second negative sense is we have already discussed, but what I want to say is that it can be either a positive risk for me in the sense that some bad items have been produced at my end, but they pass the quality test. So, obviously, it is a loss for the other person, but it may also happen that there are some good items which are rejected. So, obviously, it is a loss for me. That is why I am saying it is a positive or negative risk. So, what we want to find out is basically the beta value, and that would be given by the probability. So, now so, this is the probability that the x bar, which is the sample mean, is between the lower control limit and the upper control limit, that is less than upper control, but more than lower control, provided that the mean value has changed, which means initially you had mu naught, now it has basically changed to mu 1, where mu 1 is basically mu naught from some k sigma. This sigma is basically the standard deviation of the overall population. So, now this k technically we will consider can be plus or minus, that means if the process is going very good, obviously the mean value would basically, I would not say the word very good, consider due to some reason or the other I have slowly purchased a machine and where the filling up capability of, say for example, can of juice, that has decreased. And I want to basically change the prices also, obviously if the amount of juice in the can is changing, and I want to find out whether it is meeting my process capability. And in case, say for example, I give some extra percentage, like if you see in the bottles 33 percentage extra at the same price. So, if you consider those, obviously in that sense the k value would be positive. Now, this k value would also have an implication from the point of view of the variability, the alpha value, if you remember, z alpha by 2 minus z alpha by 2. So, they would make sense here also. Now, I want to find out the probability that x bar, I am again repeating the statement which I have highlighted, which is basically the x bar, the mean value of the sample is between lower control and upper control, provided the mean value of the whole process has changed. Now, what we need to understand is that what is the overall distribution we are looking at. Now, in the last lecture I did mention, and let me write it down clearly in the red color. So, technically x, which is the random variable, is distributed normal with mu mean and sigma square variance. Now, when I basically replace mu with x bar suffix x, n is basically sample size. So, this is the sample mean we know is distributed n with mean mu sigma square by n. So, this part we have already discussed, if you remember. So, this is what we are trying to understand. So, since x bar, which I am now trying to highlight using yellow color, since x bar is distributed with mean mu and variance of sigma square by n. So, the upper control limit now would become mu plus L. L is the coefficient into sigma by square root divided by square root of n, which was already discussed. So, in that case L, in that other example when mu and sigma were known, we had taken as 3. So, depending on the alpha value. In this case, the lower control limit is also minus part I am only discussing is minus L into sigma by square root of n. And the beta values which you see here is basically the standard deviates which you consider when you convert it into a standard normal distribution. So, let me draw it with red color. So, this is the x axis, this is the distribution with mean value of 0. So, what it means is that this capital phi means what I would like to highlight is this. So, I am using x as a general random variable. So, if I go here, so I consider x is here. So, this is the whole probability which is on the left hand side
for this case, when I basically erase it, let me erase it. When this is not right and I am using this, which means I am considering this part of the graph.
So, in this sense the calculations will be different. How it will be different? So, in the second diagram which I have just finished, this capital Phi would basically mean the cumulative distribution for all the values of the probabilities starting from minus infinity to till x. So, this will give me the total probabilities from the left to the right, and if I am finding out 1 minus that, that will give me the values onto the right. That means these values, and this one, let me highlight for ease of understanding, this one, this will give me the values onto the left. So, if I understand that from the standard normal deviate, capital Phi L minus k by square root of n and capital Phi minus of L minus k by square root of n would give me the total standard deviation of the cumulative distribution values added up from to the left or the right, depending on how you look at the standard normal deviate. So, OC curves, which is the operating characteristic curve, suppose that we are using an x bar charts with L. L is the coefficient which we have is 3, that is usually, I did not mention that. So, this is being highlighted maybe for the first time. So, this is the 3 sigma limits, which means that if I draw the curve, and if I let me use the red color for ease. So, these values are minus 3 sigma. I am using the plus minus 3 sigma considering the mu value is 0 for the standard normal deviate. So, this is the 3 sigma limits. The sample size is n and we want to, which is 5, and we wish to determine the probability of detecting a shift from mu naught to mu 1, which is basically mu naught plus 2 sigma. That means 2 sigma is the total width plus minus 2 sigma which we are considering, but it is moving on to the positive side. On the first sample following the shift. So, now consider this 3 sigma limits. Now, L is 3, K is obviously 2 and N is given as 5 because that is the basically the sample size we are taking. If you put those values, the beta value comes out to be about 0.07, which is about 0.0708. So, this is the probability of not detecting any shift which is happening, because out of the total number of such 100 pickings or 100 such observations we are taking, there would be a chance that we are not able to detect the change. So, whether that is very positive or negative would depend on how your problem has been formulated. Why I am saying that? Consider this, like you are manufacturing or are testing pacemakers. So, obviously any zero amount of fluctuation would have a devastating effect. But say for example, you are manufacturing a chair or some small machines. So, not being able to detect those shifts would not have much of a negative consequences of on the overall process. So, obviously the value of beta not detecting the shift would have different implications depending on how the problem is being formulated and what type of testing you are doing. So, continuing this, the probability that such a shift for the OC curve, the probability that such a shift will be detected on the first subsequent sample would be given by 1 minus beta. Beta would be not defecting, 1 minus beta would be the detecting. So, if it is loss from one side, it will be positive from the other hand side, which comes out to be about 92.9 percentage. So, this gives the probability that the shift will be detected, then the rth subsequent sample is simply 1 minus beta times the probability of not detecting that in each trial. So, why it is that? Because consider there are art trials. So, there are basically art such places to be filled up, art seats. Now, you have detected the shift only on the rth trial. That means, in the r minus 1 trials which have already happened, you have not been able to detect the shift. So, what is the probability of not detecting is beta in each trial. So, how many such betas would come? It will be beta for the first one, beta for the second one, beta for the third one till the rth minus 1. So, beta would be multiplied r minus 1 terms. So, it will be beta to the power r minus 1, and the last place, consider, as I was saying, there are chairs, seats to be filled up. All of them have been filled up with the value of beta. How many number of times? R minus minus 1 times, and the last one, which is the other place, has been filled up by 1 minus beta, which is a sort of distribution which we already know. I will come to that later on. So, hence the total probability would be beta to the power r minus 1 into 1 minus beta. So, the expected number of samples taken before the shift is detected by simply taking the average run length. So, that would be, so in each case I have the probabilities as beta to the power r minus 1 into 1 minus beta, and r would be the set of the number at which stage we are detecting. So, if it is beta only, so it will be beta into 1, because first state you have not been able to detect. It would basically becomes beta 2, so R2, R3, R4, R5, you will basically multiply the terms of 2 into, say for example, beta to the power 1 into 1 minus beta, plus R now becomes 3, it will be 3 into 1 minus beta into beta to the power 3 minus 1, and you will continue finding out till the last stage, which technically can be infinite. So, you find out all these values, multiply them, sum them up, that will give you the basically the information that what is the average run length, which is given by ARL. And for this example, if you have beta as given as 0.0708, then you find out the average run length as 4. That means by within the fourth one of the trials of the experiment, we are able to detect that there is a shift. Now, you want to find out the calculating the parameters of x bar and S charts. So, it is not R. So, when sigma is known, the upper control and the lower control values would be calculated from the tables depending on n value. So, the central line is C4 into sigma, which is the value over and above you will have the upper control and the lower control. The upper control limit would be given by multiplying sigma with B6, and lower control would be given by multiplying sigma with B5. So, these B5, B6 would definitely be dependent on the sample size. When sigma is not known, what you do is that you replace that sigma by the corresponding sample standard deviation or the sample standard error. So, this is which is S. So, but now obviously you will try to replace by the average value of the standard error. So, let me continue reading it. When sigma is not known, we use S, which is the average of S bar, which is the average of S for m preliminary such samples you have taken. So, you have taken first sample, second sample, third sample, fourth sample. For in each case, the standard error would be S. You try to find out the average of these 4 subsamples you have taken. The word subsample, I mean that first you have taken 5, you find out the standard error. Second, again you have taken 5, you find out the standard error. Third, you have found out the set of observations, again 5. So, you have basically m is 3, considering m is 1, 2, 3 for the set of observations you have taken. Find out S, find out the average of this. This we will use as S bar for our subsequent calculations. So, based on that, when you find out, the central values would basically be S bar. So, in the initial case, C4 into sigma was basically depending on the sample size. Now, I will use the actual S bar, and the corresponding upper value and the lower values would be basically be B4 and B3, which would be the multiplying factor based on the sample size which you are taking. For the X bar charts, now would be initially you had X double bar plus minus, I am using the plus minus both for the upper control and the lower control as K. So, this K can be either 3 or 2 or 1, as I have already discussed, multiplied by sigma by square root of n. So, now this sigma by square root of n would not be coming into the picture, but it will be replaced by S bar with a multiplying factor. So, this is what is mentioned here. So, the upper control limit becomes X double bar multiplied by the value of A3 into X bar, and the lower control limit would be basically replaced, that plus sign would be replaced by minus, and you will find out the lower control limit. And obviously, the central value continues to be X double bar, because our main emphasis is to study the X bar charts. So, here the average value does not change, only the sigma value has been replaced initially by R values, with the range values. Now we are trying to replace that with the S bar values or the S value, which is the standard error. So, we are required to construct and interpret the X bar and the S charts, not R. Remember, it is the S charts using the piston ring inside the diameter example. So, here again in the first column you have the sample number starting from 1 to 25 and the observations are given. So, what you have for the first sample, which consists of 5 observations, the values are, I am just reading them, 74.030, 74.002, 74.019, 73.992 and 74.008. From that what you need to find out? So, we need to find out X bar for each sample of size 5, the standard error for each sample of size 5. So, those are formulas are there, and based on that when you go and try to find out the X double bar, it comes out to be 74.001 and S bar comes out to be 0.0094. Now, let me highlight this value of S. So, what is important to learn is that from statistics. So, this the slide is not there, but I want to basically discuss for about 2 minutes. Now, in general in statistics we know that if I will try to use the red color, so it makes sense here. So, say for example, your mean and sigma are the values you want to study. So, now let us go step by step. In case your main concern is to study the value of mu is not known. So, I am using a minus sign on a cross sign on above, meaning it is not known to you. So, there can be two outcomes. One is sigma is known, another is sigma is not known. So, obviously, you have to replace it by the sample mean. So, what is the answer? Answer is the best estimate, which is basically known as UMVUE in statistical sense, which is uniformly minimum unbiased estimator, would be X bar n. So, this I am talking about the normal distribution, remember that. So, here let me make it much more explicit. So, in this case X bar is the best estimate for mu, either in the case when sigma is known and also in the case when sigma is not known. So, obviously, there is no problem. The second idea which I wanted to discuss here, for which I said I will take 2 minutes, is that mu and sigma are the main emphasis of study, the distribution is normal. So, let me mark it as 1. 1 means basically the study is for mu. Now, 2 is basically the emphasis where I am trying to study the standard deviation of the variance. So, I want to study this which is not known, but there are two outcomes again with this case, mu is known, mu is not known. Now, if mu is known, my actual formula to find out the best estimate from the sample, which would basically give me the maximum amount of information of standard deviation for the population, would be and in the case when the population mean is not known, now see a difference, I will highlight it. Obviously, it is very obvious from the thing which I have drawn, and use the highlighting a yellow one. So, basically for the case 1 mu is known, I use this formula. When mean is wait, let me go to the different color, so it would be easier for me. Yes, when mean is not known, I use this formula. So, it looks very intuitive. Why? So, there are two main differences in the formulas. I am talking from the theoretical point of view, from the mathematical point of view. I will come to the intuition later on, and I will mention it very briefly. So, in the first case you see that you divide by the sample size, which is n, which is here where I am hovering the pen, and in the second case we divide it by n minus 1. So, what is the reason for that? So, to answer that, let us see the formulas and the values which are inside the bracket squared. In the first case, if mean value is known, obviously you will always use the mean value, and here is where I am hovering the electronic pen. So, obviously, there is no loss of information which we have from the sample we have taken. We pick up the sample and study the sample variance only, because we are not bothered about the expected value of the population, because that is already known, which is mu. Now, in the second case where I am now hovering my electronic pen, is that when mean value of the population is not known, what do we do? First, we basically replace the mean value mu with the sample mean, which is x bar n, which we have already done here. Now, the moment you use the set of observation sample for the first time, you lose some set of information, which is known that the degrees of freedom basically you lose is 1. That is why the set of observation which you had initially now gets replaced by not by n minus 1, because the set of observation which you have in front of you lost some amount of efficiency and it becomes n minus 1. That is why the change in the formula. And remember, these the formulas which I have given here. The first one, let me use a different highlight color to make it much more obvious. The first one and the second one are extensively used for the case to find out the sample variance, provided the population mean is known in the first case and provided the population mean is not known, where we replace the population mean by the sample mean, which is x bar suffix n. So, considering this, whatever I was talking about, you find out the S, which is the standard error for each sample of size 5, find out all of them individually, find out the sums. Hence, the value of S bar comes out to be, as given here, is 0.0094. I have mentioned that, but I am again mentioning it. We have already found out X bar for each observation. So, see for example, for the 13th one, the value is 73.998. So, we have basically 25 readings, and the sum of them divided by 25 comes out to be 74.001, which I am again highlighting. So, now I want to basically do the last bit of the calculations. So, you calculate the average mean and the average standard deviation. So, as mentioned, the x double bar comes out to be 74.001, S bar comes out to be 0.0094. Based on that, when you go and do the calculation for the x bar charts, the x double bar remains as 74.001. The upper and the lower control limits would be basically be x double bar plus A3 S bar. This A3 bar is coming from the sample size information which we have, and hence the upper control limit comes out to be 74.104 and the lower control limits comes out to be 73.988. Similarly, when you do the calculations in place of R charts, now you are using the S charts. The upper control limit, when you multiply S bar with B4 and when you multiply S bar with B3, which gives you the information on the lower control limit, the corresponding respective values comes out to be 0.0196 and 0. So, using this, you have basically been able to replace the R charts with the S charts, which is the standard error, and that will give you much better set of informations and better set of informations about the process control, provided one important thing which I did mention, I am again mentioning, is that the sample size for each such small readings keep changing depending on the about type of experiment we are trying to do. So, with this I will end this class and continue more discussions about the process capability charts later on in the later lectures. Have a nice day. Thank you very much.